All right, guys, welcome back. So today we're going to talk about really how Earth's geologic record is a great piece of evidence for biological evolution. And if we look at the fossil record, right, this really is going to chronologically tell us the evolution of life on Earth, or at least as best as it can. So let's talk about what the fossil record is. When we look at fossils, right, they are preserved remains that have been turned into rock by time and pressure, or they're casts of organisms that once lived. So leaf casts and things like that, right? So impressions. Now, most fossils are found in sedimentary rock. We can find other fossils in things like amber, so tree sap, and things like that, but the bulk of the fossils that we study are coming out of sedimentary rock. And if you know anything about how sedimentary rock forms, we're looking at water rushing across land surfaces. It takes sediment, dirt, rock, that kind of thing along with it. And as it gets to places like ponds, lakes, oceans, where that water slows down, that sediment then falls out of solution to the bottom of that body of water and continues to pile up. The more that sediment piles on top of itself, the more pressure that builds and the harder that rock layer eventually becomes. So, sedimentary rock, assuming that those rock strata, those layers, have never really been disturbed, you get this really nice chronological order of geologic time. And if any organisms happen to get stuck within that sediment at that time, they can potentially fossilize. So when we look at this, it's sort of this law of superimposition. What does that mean? Is that those sediments are superimposed or layered one on top of the other, so that the layers at the bottom of that rock formation are going to be older than the layers as you get closer to the surface. Now, there's some caveats to this. Earth processes, mountain building processes, for example, can take these rock layers and shift them, all right, can potentially flip them completely upside down. So there's some other things that we need to look at to get a more accurate timetable, but using those rock layers, if you know what you're looking for, is a great way to relatively date one layer from the next. So that's one piece. The other thing that comes along with some caveats to the fossil record, though, is that it's going to bias species that exist for a long period of time, right? In order for these species to get fossilized, they have to get trapped in the sediment. And the longer that they exist on Earth, the more likely you're going to have those organisms happen to die next to a watery environment, happen to get covered up in enough time, short enough period of time by sediment to actually become fossilized. It becomes the fact that those organisms not only have to exist for a long period of time, but they also have to be abundant and relatively widespread. Again, it's statistics. The higher the number, the longer they exist, the more likely they find themselves in the environment conducive to fossil building. Third piece to this is that it's also going to bias organisms who have hard parts. Think about what most fossils are. They're bone. You're not getting fossils that contain fleshy parts. So organisms that don't end up having those hard parts are not completely excluded from the fossil record, but it's much less likely for them to be fossilized without that. And then the actual discovery of the fossil itself also tends to be a matter of chance, although the more and more we find things, the more we can start making predictions about where we might find more. So I mentioned to you just a second ago, the fossil record's a great relative date. But if we want to accurately date these fossils and know exactly what their time frame is, then we have to use radiometric dating. And radiometric dating, even in itself, has a degree of uncertainty. So when we look at radiometric dating, we're talking about a method for determining the age of rocks, fossils, really any sort of material based on an absolute time. And the way that this works is everything on Earth contains a certain level of radioactive isotopes. Most of you are probably familiar with, if you've come across radiometric dating before, with carbon-14. So carbon-14 is an isotope of carbon, and all of these radioactive isotopes have a known half-life. And what does that mean? A half-life is the number of years it takes 50% of that sample to decay, to break down into something else. And so we can measure that. So when we look at carbon-14, for example, it decays into nitrogen-14. We know its half-life occurs every 5,730 years. Okay, so when that sample is originally produced, it's going to have 100% of its carbon-14 atoms. There will be no nitrogen-14 present. After 5,730 years, we're now down to 50% of that carbon-14 left. We go another 5,730 years, we're now down to 25% of the carbon-14 left. Go another half-life, we're now down to 12.5%, so on and so forth. So it breaks down in half every time you go through a half-life. So what we can do is use sensitive equipment to measure the amount of radioactive isotopes present in a sample. We have to be smart, though, about using the appropriate radioactive isotope. So for carbon-14, for example, it's really only good at dating materials up to 75,000 years old, which, when we look at geologic history, really isn't all that old at all. Dinosaurs are going to be way before this. So there's a whole host of radioactive elements that we can choose from. But we'll often use the fossil record as a means of giving us some relative date so that we can choose the appropriate radioactive isotope to start trying to come up with a more absolute date on how old that particular product is. Nice thing about the fossil record when we find it are these things called transitional fossils. They're not necessarily overly abundant, but they're incredibly exciting when we find them. So transitional fossils really are just these fossils that we find in layer upon layer upon layer. So oldest being at the bottom, newest being at the top, and we can see these chronological changes in their structure over the course of that fossil record. So this is just an example of mammals known as tetrapods, and we're looking at these transitional changes in the back of their jaw structure over time. And we're able to see these show up chronologically in the fossil record, which is really kind of cool. Another one, and I'll just skip back here for a second, Tiktaalik was a really exciting transitional fossil because if you look closely at Tiktaalik, he looks very much like a fish in terms of its head structure and things like that, sort of like a cross between a fish and an alligator. But he had limbs. And so Tiktaalik is one of those transitional fossils that started giving us some interesting evidence for how life got out of the oceans and got onto land. So take some time, look that guy up. It's a pretty interesting story. So I've been alluding to this idea of geologic time records. And what geologists have done, and scientists have, biologists, I should say, now utilize as well, is the division of Earth's history based on these major changes that we see in the fossil record. And so what they've done is successfully broken up Earth's history into these eons, eras, periods, epochs. And we look through the fossil record for major changes as places to superimpose these divisions onto that fossil record. So most of the major boundaries between these geologic divisions correspond to major extinction events. So remember, extinction is just talking about large numbers of, well, mass extinctions are large numbers of organisms that seem to all die out at the same time or within a relatively short period of time. So they use these as major boundaries between these divisions. So here is the table out of your textbook. You guys are going to be using this for a project coming up that I'll explain a little more later, but what we're looking at are all of these major breakpoints. But if you look overarchingly, here are the eons, okay? And these first two eons, if you follow the way that they're broken up down here, all right, we just start seeing some life showing up right here. Okay, so here's 4.6 billion years. All right, and it takes until somewhere between 6 and 5 billion years, million years, excuse me, before we really even start seeing life. So there's hundreds of thousands of years of no life at all. The amount of time that life is actually spent here on Earth is incredibly short for the overarching geologic time that exists. And this clock analogy is a great way to look at it. Your project is going to do something similar to this, where you're going to superimpose the geologic record onto a calendar and just be able to get a sense of how much time has passed as a scaling activity for life on Earth. And if we look at the clock analogy that your textbook utilizes, right, we don't even start getting prokaryotic life until we're a quarter of the way into the hour. Humans are here for like a nanosecond. And so this geologic time is huge. So giving you these sorts of scales to kind of play with and look at just gives you a better sense of how fleeting life kind of really is here on Earth and how quickly um, evolution really has occurred when you take into the context that the Earth is 4.6 billion years old.